Okay, now we're going to talk about graphing motion. So our objectives are to construct and interpret graphs and diagrams of position, velocity, and acceleration versus time, and then determine and interpret the slopes and the areas of those motion graphs. So again, graphically, we're simply going to look at motion. Now, there's a couple different ways we can do this. First of all, we have something called a particle diagram. And probably the easiest way to think about it is if you had a car driving down the street with an oil leak, and it's going to leak oil on a regular interval. So the dots can be used to represent the motion of the vehicle. So if you look at the dots, you can then make conclusions about the motion of the vehicle. So this is one of the easiest ways to look at motion. Another thing, in the laboratory, we can also create these using strobe lights in a darkened room and moving balls. So therefore, as the ball moves, when the strobe light comes on, it's going to take a picture and record an image of where the ball is. That's how a lot of the falling ball pictures are created for your textbooks and stuff like that. So let's take a look at these. What can you say about each case? Let's look at X. The dots are all equally spaced. Obviously the object's moving because the dots aren't in the same place, and since they're all equal distance, we know that that's constant speed in a straight line, so constant velocity is also fine. If you look at Y, the dots are getting progressively farther apart. That means the object is accelerating. Since it's speeding up, it's a positive acceleration. Now in Z, look what happens is the dots are getting closer together. That means that's a negative acceleration. The object's stopping. Okay, now a position time graph, sometimes called a displacement time graph, is going to show displacement versus time. So let's take a look at what each section shows. So the first angled section shows constant velocity. The displacement is changing, but it's always changing by the same amount. So therefore that's a constant velocity. The top interval, well, it stays at 5 meters the whole time. So what that's actually showing you is rest. And then coming down the backward slope, we're also seeing a constant velocity. We're also seeing a constant velocity, We're also seeing a constant velocity there, but in this case it's a negative velocity. You're going back to your original starting point. Now here's the key thing about a position versus time graph or displacement time graph. The slope gives you the velocity. If you think about velocity is change in displacement over time. Well, slope is going to be rise over run, which is going to be change in displacement divided by time. So if I look at interval A numerically, let's take a look at it. Units will also help you in this. If I go to find the slope of A, it's 5 meters divided by 5 seconds, and I get 1 meter per second. So even if you forget what the slope tells you, you get units of meters per second. Units of meters per second are velocity. Now, a velocity time graph shows velocity versus time, and it's related to the position time graph by slope. So if you look at these two graphs go together. It's the same graph we had on the previous page, and they actually go together. If you look at it from 1 to 5 seconds, the speed is 1 meter per second. If you look at from 5 seconds to 10 seconds, it's at rest, so the speed is 0. And then the speed from 10 seconds to 12.5 seconds is negative 2 meters per second. So they're actually related. Key thing to remember, a negative velocity is a negative slope. That's why that last area is negative. Now, area under velocity time graphs gives you the change in displacement. So that's kind of neat. But again, you can kind of figure it out from that. Velocity times time, well, meters per second times seconds is going to leave you with just meters. So it actually gives you the displacement. So if I look at interval A, I'm going to do that area right there just to do a sample one to make sure that it works. I'm going to simply do the area of that, which is going to be 1 meter per second, that's the height, times 5 seconds, which is the base, gives me 5 meters. And I can look at my graph above that if I have it, and I can check it. What's the displacement at 5 seconds? Well, by looking at that line going up and over, it's also 5 meters. So again, the math backs up what our brain tells you. Now let's do a sample problem. The slope of a velocity time graph gives you acceleration. I'm just going to tell you that and remind you of it. Excuse me. So what's the acceleration for the first 4 seconds? So A is equal to delta V over T, which is rise over run, which is 10 meters divided by 4 seconds. I just simply get those values off the graph. I get 2.5 meters per second squared. Now next, I want to know total displacement for the entire 6-second interval. So now, velocity times time is going to give me displacement. So it's the area under the curve. Now, I can't do all that in one step, so I'm going to break it up into sections. A is a triangle, B is a rectangle. You can easily do that. So divide it into sections that you can easily handle. A is 1/2 base times height. 1/2 4 seconds is the base, times the height of 10 meters per second gives me 20 meters. Now look at an interval B, which is just a rectangle, and we know rectangle is simply base times height. So therefore the base is 2 seconds, the height is 10 meters per second, so it traveled 20 meters during that interval for a total of 40 meters. Now if you look at both of those values being 20 meters, but one took 4 seconds, one took 2 seconds. The reason for that is during the interval A, the object was accelerating. So the average speed was 5 meters per second. 5 times 4 is 20. So again, the math backs it up. Now, if you take the slope of a velocity time graph, it will give you the acceleration. The area under the acceleration time graph will give you delta V. So if I look at this 10 meters per second squared, gravity, if I look at that, and I'm considering it to be a positive value, so if I take the slope of that velocity time graph, that's not a velocity time graph, excuse me. So if I take the area under the curve of the acceleration time graph, so let's take a look at that. So if I want to figure out what the velocity was for the first second, it's simply base times height. 1 times 10 is 10 meters per second. Remember, your 10 meters per second squared times seconds, so one of your seconds cancels out. So for 2 seconds, it's going to be 2 times 10, 3 times 10, etc. Now, how do you go from one graph to another? And here's kind of a neat pattern you can get out of this. Slope. Slope goes that way. So in other words, the slope of x over t is equal to v. The slope of v over t is equal to a. So when you simply take the slopes, you're simply going the other way. Now let's take a look at the area goes the other way. The area under a velocity time graph gives you position. The area under an acceleration time graph gives you velocity. Now, from this, the best type of graph you can get is a velocity time graph, because it allows you to get everything. It allows you to get position, it allows you to get velocity, and it allows you to get acceleration, all from a single graph. Now, sketch a graph for an object moving with constant velocity. Now, when I approach a problem like this, I always think of a real-world case of constant velocity. And probably the most common one that I think of immediately is cruise control. So what's happening on cruise control? Well, on cruise control, I'm covering the same amount of distance each unit of time. So it's going to be a linear relationship. Now, since I'm at constant velocity, it's not changing, so therefore it looks like that. Now, constant velocity, as opposed to acceleration. Well, acceleration is delta v over t. Delta v is 0. So it looks like that the entire time. Now, that's a case we encounter a lot. The other case we encounter is constant acceleration. The most common case of that is free fall. So let's think about it. As an object falls, it gets farther and farther and farther apart. So it's a parabola. That comes from the x is equal to 1/2 at squared equation. That's the reason it becomes a parabola. Now, since it's moving and it's getting bigger each time, but it's a constant change, the velocity looks like that. The velocity is changing, but it's always changing by the exact same amount. And then finally, your acceleration value stays the same value the entire time. So it looks like that. Okay, let's look at a sample. Which graph best shows a car on cruise control? Now, if a car's on cruise control, we know the acceleration is equal to 0. Now, this is a distance time graph. Now, first of all, look at case 1. Case 1 is not moving, so therefore that's not right. Case 2 is moving for a little while, then it stops. You're not going to stop when you're on cruise control. So we're down to either case 2 or case 4. In case 2, our distance is changing by the same amount all the time. That's cruise control. 4 would be an object that's accelerating. So now, which graph best shows a block sliding down a frictionless inclined plane? Well, if I'm sliding down a frictionless inclined plane, I am going to accelerate. And it's frictionless, so therefore it's not going to stop accelerating. So therefore, since A is positive, the best answer is number 4.